Let's look at this problem. In this problem, we have this block right here. Its gravitational center is given. It is connected by pins to two links. These two links, AB and CD, are weightless. We can neglect their mass, which is very important. If we know that the link CD is rotating with the angular velocity of 6 radian per second, and at the same time it is subjected to a couple moments, 450 Newton meter, we need to determine several things. We need to determine the force developed in link AB, the horizontal and vertical components of the reactions at pin D, as well as the angular acceleration of link CD. So let's see how we approach this problem. By looking at it, we can simplify it a little bit and realize that link AB is a two-force member, which means that the force in link AB has to be along the orientation of AB. However, that's not the case for link CD. Link CD is not a two-force member because even though it's subjected to forces only at 2 points C and D, it is also subjected to a couple moments. Therefore, at point D, we will have two unknowns. So that's the first thing we observe, finding the two force members, trying to simplify the situation. Second thing is that to recognize that for the block, it is undergoing curvilinear motion. So it is still translation, but it's curvilinear motion. In other words, the path of point G is following a circular path, but it's still translation, except that now the acceleration at point G has two components now, AX and AY. So if we draw the free body diagram of block, of this block right here. So this is the point G. It is subjected to its weight, which is mg 50 times 9.81. And then at point B, which is right here actually, it is 0.1 meter away from point G. So at point B, we only have one horizontal component, FAB, because link AB is a two-force member. And here at point D, we have two components, dx and dy, because link CD is not a two-force member. And if we also draw its kinetic diagram, this is again point G, then we will have two components, MAX, which is 50 times AX, and MAY, which is 50 times AY. So at this point, we realize that we can only write three equations of motion for block BD. However, we have five unknowns. We have FAB, AY, AX, DX, and DY. So we don't have enough equations. Therefore, we need two more equations. So one thing that might be obvious is that because this block BD is doing translation, that means that for every point, the acceleration, the motion is the same. So they will always have the same velocity, same linear velocity, and same linear acceleration, which means that at point D, this point D will have exactly the same AX and AY acceleration, just like at point G. Now, because point D also belongs to rigid body CD, and this link CD is doing rotation about a fixed center. So based on simple kinematics, we can determine that for point D, these two components, AX and AY, AX is the same as normal acceleration AN, which equals to omega squared times r. And in this case, omega is known as 6 squared times r. The length of the link is 0.6 meter, and that equals to 21.6 meter per second squared. So as you can tell, now we have already taken care of one of the unknowns. So this unknown is actually determined to be 21.6 meter per second squared. So that's good news, but we still need to find one additional equation or solve for one additional unknowns. Let's look at this AY right here. This AY right here equals to the tangential acceleration, which equals to alpha r. R is known, but alpha is not. So this equals to 0.6 alpha. Alpha is the angular acceleration of this link that we also need to solve for. So instead of finding some information, we actually introduced one more unknown, which is alpha, which is actually related to AY. So if you solved for alpha, you found AY. So this is the free body diagram of block BD. But if we draw the free body diagram of link CD, this is what we have. It is subjected to a couple moments of 450 Newton meter, and also CX CY because we have a pin support at point C. Now, because of action and reaction, we need to draw dx and dy in these directions. So let's see what we can solve from this free body diagram. If we summarize the moment about point C, what we have is we have counterclockwise is considered positive, therefore we have dy times the moment arm of 0.6 minus the known moment 450 Newton meter, and this actually equals to 0. So if you argue how come this equals to 0, this comes from this sentence, neglect the mass of links AB and CD. This is not because link CD does not have angular acceleration. It does have angular acceleration. However, it has zero mass. If it has zero mass, it has zero mass moments of inertia about any axis. Therefore, if you summarize the resultant moment, it's always 0. So equilibrium equations actually apply here for weightless objects. So this is not an equation of motion, not because link CD is not moving. It's because link CD has negligible mass. So from there, we can solve for dy. dy equals to, in this case, 750 Newton. So now dy has been solved for. Let me substitute that in. Now, if we go back to the free body diagram of block BD, we realize that we only have 3 unknowns left. We have FAB, AY, and DX. So from there, we can start writing the 3 equations of motion for block BD. Excuse me for writing in a disorganized way. I'm trying to fit everything into this screen. So resultant force along the x direction for block BD, we have FAB plus dx equals to MAX, which equals to 50 multiplied by 21.6. Resultant force along the y direction equals to the weight force 50, which is negative 50 times 9.81 plus 750, which equals to MAY, which equals to 50 times AY. For the moment equation, you can do resultant moment about point G equals to 0. That's fine, because this is a translation and G is the gravitational center. Or you can do resultant moment about point D, just because we have 2 forces at point D. And this does not equal to 0. So this equals to the weight force have moment about point D, and that equals to negative 50 times 9.81 times the moment arm of 0.1 meter, this distance right here. All right, plus, so actually this is plus, actually minus here. FAB has moment about point D with a moment arm of 0.4 plus 0.4, 0.8 meter. And that equals to the kinetic moment about point D. And in this case, we have 50 AY and this right here, these two MAs both have a moment about point D because the location of these two MAs are both at point G. Therefore, for the horizontal acceleration, it is causing clockwise rotation about point D. So this equals to negative 50 times 21.6 times the moment arm of 0.4 meter. And this component right here is also causing clockwise rotation about point D with a moment arm of 0.1, and that equals to 0. So three equations, three unknowns. So the three unknowns left are FAB, dx, and AY. And from these three equations, we can solve for all three of them. Therefore, we have FAB equals to 634 Newton, dx equals to 446 Newton, AY equals to 5.19 meter per second squared. And then if we know AY, substitute it into this equation to solve for alpha, and alpha equals to 8.65 radian per second squared. That's the angular acceleration of the link CD. So now we have solved for everything that we were asked to solve for.